3 lectures, we have been discussing the solution of the one-dimensional Schrodinger equation for the particle in a box of dimension A, and we also considered before that the free particle problem. Those were two important problems in quantum mechanics. Today, we will be starting our discussion on the linear harmonic oscillator problem. This is one of the most important problems in quantum mechanics and allows one to understand very clearly the relationship between classical mechanics and quantum mechanics. The plan is that we will first give the solutions of the Schrodinger equation before doing the detailed mathematics associated with it, and then we will discuss the physics of the solutions and obtain results which correspond to the classical oscillator. Once we have understood the consequences of the solution, we will then do a little bit of algebra and solve a differential equation and obtain the exact solution of the Schrodinger equation, of the one-dimensional Schrodinger equation corresponding to the linear harmonic oscillator problem. So, let us start with our familiar one-dimensional Schrodinger equation which is given by I h cross, as we all know, delta psi by delta t is equal to h psi, where h is the Hamiltonian, the operator corresponding to the total energy, and this in the one-dimensional case is given by minus h cross square by 2 mu delta 2 by delta x square plus v of x psi, which is a function of x and t. Now, we have solved this equation for the free particle, where v of x is 0. We have solved this equation for a particle in a box problem, as I just now mentioned, confined in a one-dimensional infinitely deep potential. Today, we will give the solutions corresponding to the harmonic oscillator problem, which is equal, for which this is v of x is given by half mu omega square x square. We know the mu is the mass of the particle, omega is the classical frequency, and x is of course the x coordinate. This is the classical expression for the potential energy corresponding to the harmonic oscillator, and we will write down first the solution of this equation corresponding to this potential. Once again, since v is a function of x only, does not depend on time, so we can use the separation of variables to solve this equation, and if we carry out this separation of variables, then you will have psi of x of t is small psi of x times a function of time, which can be shown to be equal to minus e I e t by h cross, where psi of x satisfies the following eigenvalue equation: minus h cross square by 2 mu d 2 by dx square. Now, it is the total differential plus v of x psi of x. This we had done even in our last lecture. Psi of x is equal to E times psi of x. This is the time independent Schrodinger equation. Actually, this is an eigenvalue equation, as I had mentioned last time, that h psi of x is equal to E psi of x. E is a number and h is the operator. and for a given potential we have certain discrete values of E. For the particle in a box problem, we had seen that the energy eigenvalues were something like this: E is equal to E n is equal to n square of E 1. We got discrete energies in a box. For the free particle problem, all values of E greater than 0 were allowed. So, we will solve this equation when V of x is equal to half mu omega square x square. So, we rewrite this equation for V of x is equal to half m omega square x square, and if we do that, let me align this properly. So, we will have d2 psi by dx square plus 2 mu by h cross square E minus half mu omega square x square psi of x is equal to 0. This is the, you just rearrange the top equation and you will get this particular equation. So, let me put it in a little convenient form. I introduce a dimensionless variable xi which is proportional to x. Gamma is the proportionality constant, and I will decide on its value little later. So, d psi by dx, if I introduce this independent variable, so d psi by d xi into d xi by dx, which is equal to gamma. I differentiate it again, I will get d2 psi by dx square is equal to d of d xi of this multiplied by d xi by dx. So, this will become d2 psi by d xi square multiplied by gamma square. So, what I do is I substitute this in this equation and obtain, please see this, d2 psi by d xi square multiplied by gamma square. I take 2 mu inside, so I will get 2 mu E by h cross square minus half mu omega square, and then I multiply by 2 mu by h cross square. So, 2 mu by h cross square, and x here is xi by gamma. So, xi square by gamma square. Now, psi is a function of xi now. So, I divide by gamma square. So, I will get, if I divide the whole equation by gamma square, so d2 psi by d xi square plus, let us suppose I write this as lambda, where lambda is defined to, when I have 3 equal to sign here, it implies defined to be equal to. So, this will be equal to 2 mu E by h cross square gamma square. Then if you see this carefully, then 2 cancel out, mu square omega square by h cross square. So, this will be lambda minus mu square omega square by h cross square. Then gamma square comes here. So, it will be xi square by gamma to the power of 4. So, there is already a gamma square here. So, I multiply this by gamma square. So, it becomes gamma to the power of 4. So, this multiplied by psi of xi this is equal to 0. I still do not know the value of gamma, I have not yet defined it. I now choose gamma such that this quantity is equal to 1. So that the coefficient of xi square is unity. So I choose gamma to the power of 4 is equal to mu square omega square by h cross square. So if I take the square root, then I will get gamma square is equal to mu omega by h cross, and so therefore you will have gamma is equal to, I define this equal to mu omega by h cross. This is the definition of gamma. So if I choose gamma equal to under root of mu omega by h cross, then this quantity which I have encircled with blue becomes 1, and so the Schrodinger equation becomes, if you see this carefully, that the Schrodinger equation then becomes d2 psi by d xi square plus lambda, and this quantity is 1. So, this is xi square, psi of xi is equal to 0. So, I have the two definitions. The one definition is that of gamma, what xi is equal to gamma times x, where gamma is equal to square root of mu omega by h cross. This is a dimensionless quantity. X has the dimensions of meters. So, gamma has the dimension of meter inverse, and lambda is defined to be equal to 2 mu e by h cross square, then gamma square. As you can see here, lambda is equal to 2 mu e divided by h cross square gamma square. So, this becomes mu omega by h cross. So, mu cancel out. So, you will get 2 e by h cross omega. So, therefore, we can reduce the transform the Schrodinger equation, we can transform the Schrodinger equation to this particular form. Now, we will later solve this equation. We will find that if I assume that psi of x or psi of xi is made to go to 0 as x or xi tends to plus infinity or minus infinity, this is known as the boundary condition. These are known as boundary condition. So, if I impose the condition that the wave function has to go to 0 as x goes to plus infinity or minus infinity, only then it will be a square integrable function. Only then it will be a well behaved function. So, if I impose this boundary condition, we will find that lambda must take only an odd integer 2n plus 1, where n is equal to 0, 1, 2, etc. These are the eigenvalues of this equation. This concept must be clear. These are the eigenvalues of this problem. That is, only for lambda equal to 1, 3, 5, 7, 9 and so on will the solution of the Schrodinger equation be well behaved at x is equal to plus infinity and x is equal to minus infinity. for all other values of E, there will exist a solution, but which will blow up at infinity. So, therefore, these are the eigenvalues of the problem, and since lambda is equal to 2E by h cross omega, so this means that this quantity must be equal to 2n plus 1, and therefore, this gives us the important result that the energy eigenvalues are quantized. We will have E is equal to E n, n plus half h cross omega. I must repeat, I have not solved this equation yet, but I plan to do that later in one of the later lectures. Today, I will just give you the solution and try to make you understand the importance, the physical significance concept behind the solution. For these values of E, the eigenfunctions are given by psi n of x is equal to some normalization constant n, and these are h n of xi e to the power of minus half xi square. These are the normalized eigenfunctions corresponding to the linear harmonic oscillator problem. This is of course a Gaussian function, and h n of xi are known as the Hermite polynomials after the French mathematician Hermite. These are known as Hermite polynomials. In fact, h 0 of xi is equal to 1, h 1 of xi is equal to 2 xi. Maybe you have read these in your mathematics class. H 2 of xi is 4 xi square minus 2, and h 3 xi is 8 xi cubed minus 12 xi. I wrote 4 of them to show that they are all alternatively even and odd. This is even, this is even, this is odd, and this is odd. These are known as Hermite polynomials, and the normalization constant, I think you must remember this, gamma divided by 2 to the power of n, n factorial square root of pi. There is one important property that may help you to remember the Hermite polynomials, that h n of xi, the maximum power of xi will be xi to the power of n, and the coefficient of that will be 2 to the power of n. So, please see this, for n equal to 0, 2 to the power of 0 is 1, for n equal to 1, this is 2, for n equal to 2, this becomes 2 to the power of 2, so 4 xi square, n equal to 3, this becomes 8. For h 4 of xi, for example, you can write down immediately that the first term will be 16 xi to the power of 4, and so on. So, the coefficient of xi to the power of n in h n of xi is always 2 to the power of n. So, therefore, these are the discrete eigenvalues of the problem, and these are the normalized wave functions of the problem. So, therefore, if I plot the potential, so it will be the parabolic potential. So, this is my V of x and this is x. So, the discrete energy states are half h cross omega, 3 halves h cross omega, 5 halves h cross omega, and so on. And the first one is just a Gaussian function. The second one is a Gaussian function multiplied by xi. So, it will be something like this. And then this will be something like these are alternately symmetric, antisymmetric, symmetric. I will prove that theorem little later. So, this is my V of x is equal to half mu omega square x square. So, we have now proved that we have the expressions for h psi n is equal to E n psi n. N takes values 0, 1, 2, 3 to infinity. So, there are infinite number of wave functions and E sub n is equal to n plus half h cross omega, and psi n of x, as I told you, these are n sub n h n of xi e to the power of minus half xi square, where xi is equal to gamma x. As I had discussed in my last lecture, these wave functions form a set of orthonormal functions, and the coefficient n sub n, that is orthonormal function means psi m star of x psi n of x dx is equal to 0 if m is not equal to n. All limits as before are from minus infinity to plus infinity, and when m is equal to n, mod psi n square dx, I can always choose the value of n sub n such that this integral is 1. And in fact, the n sub n are chosen in such a way that you have this condition that minus infinity to plus infinity psi m star of x psi n of x dx is equal to the Kronecker delta function. So, this is equal to 0 if m is not equal to n and is equal to 1 if m is equal to n. So, this condition is known as the ortho normality condition. This condition and these wave functions will satisfy this orthonormality condition. There was yet another condition that we had said, and that was the completeness condition, that summation psi n star of x prime psi n x summed over n, this is equal to delta of x minus x prime. This is the completeness condition. This tells us that any well behaved function of x, like phi of x, can always be expanded in terms of this complete set of something like the Fourier series, that in a particular interval any well behaved function can be expanded, as you may have already read, in terms of the Fourier series. Similarly, in the space defined by from minus infinity to plus infinity, the Hermite Gauss function that I had written down, the Hermite Gauss functions are These are known as the Hermite Gauss functions. So, the Hermite Gauss functions form a complete set of functions that any arbitrary function, any arbitrary square integrable single valued function can be expanded in terms of this function. And therefore, the general solution, the most general solution of the one dimensional Schrodinger equation, that is I h cross delta psi by delta t is equal to h psi, where h corresponds to the linear harmonic oscillator problem, will therefore be given by psi. When I write capital psi, that means it is a function of x and time. When I write small psi, then that is a function of x only. So, psi of x comma t is equal to a superposition, that is C n, just as we had done for the particle in a box problem, e to the power of minus I e n t by h cross. But in this case, and the summation is over n equal to 0, 1, 2, 3 to infinity. In this case, I know the values of E n. E n is equal to n plus half h cross omega. So, this becomes equal to summation C n psi n of x e to the power of minus I n plus half omega t. This is the most general solution for the harmonic oscillator problem, that is, any state of the oscillator can be described by this sum, and this is how it will evolve with time. So, let me give you an example. So, let us suppose I tell you, and I will give you an example with which all of you will be familiar. Let us suppose I know the wave function at time t equal to 0. So, this we know. I know the state of the oscillator at time t equal to 0, and I want to find out that how will the wave function how will the wave function evolve with time. That is my question. So, I substitute t equal to 0 here, and I will get C n psi n of x. I know this function. So, using this equation, I will find out C of n. I know psi of x comma 0, I know psi n of x. These are the Hermite Gauss functions. So, I will now use the orthonormality condition to determine C of n, and then I will substitute it in this equation and carry out the summation. In most cases, it is not possible to obtain an analytical form, but in some situations it is possible to sum it analytically and give a physical description of the system. So, I come back to this equation, and and I am sure all of you know this. Let me write this. Psi of x comma 0 is so much. So, how do I find this? I am sure you know this, we have done this before. I multiply both sides by psi m star of x. So, I multiply both sides by psi m star of x dx and carry out the integration from minus infinity to plus infinity. So, the left hand side will become all limits are from minus infinity to plus infinity, psi m star of x psi of x comma 0 dx is equal to summation c sub n integral psi m star of x psi n of x dx. This we know from the orthonormality condition, this is equal to delta m n. So, therefore, this equation becomes, so right hand side becomes C n delta m n. M is a fixed number, n is a running index, n goes from 0 to infinity. So, in this series only the n equal to m term will survive and all the other terms will be 0. So, this will be equal to C's of m. So, C of m will be given by this, and so therefore, once I know C of m, so I know that C of n is equal to minus infinity to plus infinity psi m star, sorry, psi n star now of x psi of x comma 0 dx. If I know C of n, then in principle, not in principle, actually I can substitute it, psi of x t is equal to C n psi n of x e to the power of minus I n plus half omega t. There is one more thing that I would like. So, therefore, if I know psi of x comma 0, I can find out C of n. Once I know C of n, I substitute it here and carry out the summation. Before I proceed further, let me mention one more thing, that psi of x comma 0, we wrote that as C n psi n of x. The complex conjugate of that is psi star x comma 0 is equal to C n star psi n star x. So, if I multiply this by this, then I have to multiply this sum with this sum, so that this n does not get, both summations are over n. This does not get confused with this, I replace n here by m. So, that what I am trying to tell you is psi star x comma 0 multiplied by psi of x comma 0. If I multiply the two equation and integrate, so I have two sums, 1 over n and 1 over this n, but this n should not get confused with this n. So, I will write here as m C m star C n psi m star x psi n of x. If I multiply by dx and carry out the integration, then these are the only two quantities which depend on x. So, I can carry this out. But the limits are all of course from minus infinity to plus infinity. This, from the orthonormality relation, we know that this is equal to delta m n. So, only the m equal to n term will survive, and therefore, this will be modulus of C n square. So, therefore, if initially I choose a wave function which is normalized, then mod Cn square is 1 summation 1 2 3, and therefore, we can interpret Cn square as the probability of finding the oscillator in the nth state. So, Cn square will be the probability of finding the oscillator in the nth state. And this does not change with time. So, when I write psi of x, this is a characteristic of quantum mechanics, that a system can be in a superposed state. So, it is a superposition of various states. So, let us suppose C1 is equal to 1 over root 2, C2 is equal to 1 over root 2. So, only two states are superposed. The probability of finding in the n equal to 1 state is half, probability of finding in the n equal to 2 state is half. So, the eigenvalue corresponding to this is 1 plus half, that is 3 by 2 h cross omega, and the eigenvalue corresponding to 5 by 2 h cross omega. Then you ask yourself the question that does the oscillator have a given fixed energy? The answer is no. There is a half probability of finding 3 by 2 h cross omega. That is, if you make a measurement of energy, then there is a half probability of finding 3 by 2 h cross omega, and there is a half probability of finding 5 by 2 h cross omega. This is the concept of superposition, which is one of the most important parts of quantum mechanics, one of the important aspects of quantum mechanics. It can be in a superposed state. Let me take another very simple example, that C1 is equal to, let us suppose, 1 over root 3, C2 is equal to say 1 over root 3, and C3 is 1 over root 3. I have taken a very simple. So, there is a 1/3 probability of finding it in E1, 1/3 probability of finding in E2, and 1/3 probability of finding in E3. And these probabilities will not change with time, and therefore, these states are known as stationary states. The probability of finding them in that state will not change with time. However, when I wrote down psi of x comma 0 is equal to C n psi n of x, and psi of x comma t will be equal to, how will it evolve with time? Psi n of x e to the power of minus I n plus half omega t. The phase factor will change. The coefficient of Cn, the coefficient of Cn, the modulus square of that does not change with time. So, Cn times this, Cn times the exponential factor, let us suppose this I write as phi. So, minus I phi, the modulus square of that is mod Cn square. So, that does not, phi depends on time, that does not change with time, but different states will superpose with different phases at different times, and I will tell you a consequence of that. Now, let us suppose that I choose a system, I have my initial oscillator in this state, that psi of x comma 0 is equal to, say, this is a normalized function gamma under root of pi e to the power of minus half xi minus xi 0 whole square. If xi 0 is 0, then this is just the ground state wave function. But I assume that xi 0 is finite, and this is the initial state of the system. At time t equal to 0, the wave function describing the harmonic oscillator is given by this equation. And my question is that if this is so, then how will this wave function evolve with time? And the answer is simple. I first calculate C sub n, that is psi n star of x psi x comma 0 dx. The algebra is a bit complicated, involved. It is given in many books, including my book with Professor Lokanath. And the final result is that it's slightly complicated, square root of n factorial half xi square raised to the power of n by 2 e to the power of minus quarter xi naught square. So, this is if psi of x comma 0 at time t equal to 0 is given by this expression, then the coefficient C of n, if you substitute this expression in this and use for psi n of x the Hermite Gauss function, carry out the integration from minus infinity to plus infinity. It is little cumbersome, but very straightforward, and it is given in many books, including in my book, that is myself and Professor Lokanath, S. Lokanath, Quantum Mechanics, and published by Macmillan. So, all the detailed steps are given there. This is the 5th edition. Now, the next step will be to substitute this. So, I want to now find out how it will evolve with time, psi of x t. So, what I will do is I will substitute in this equation, this has been the general recipe, and sum it. So, I substitute this expression here and carry out this summation, and it is one of those rare occasions that you can actually sum this series, and the final result is very straight, very beautiful. So, you will get, if I sum that and take the complex conjugate of that and then multiply, that is mod psi x t square is equal to gamma by root pi e to the power of minus xi comma xi 0 cos omega t whole square. So, this is the probability distribution p of x comma t dx represents the probability of finding the particle between x and x plus dx. So, that probability distribution function is actually oscillating with time, and I will show this to you in a moment graphically. If I calculate the expectation value of x the average value of x, then that, as we all know, was psi square x dx. I multiply this by x. You may remember that xi is equal to gamma x. You can carry out this integration very easily, just a few steps, and you will find that this will be equal to x naught cos omega t. And similarly, if you calculate x square, so you will find that mod psi square x square dx, you will find that this is equal to x naught square cos square omega t plus 1 over 2 gamma square. I would request all of you to work out these integrals. This is very straightforward, and you only have to use the integral that e to the power of minus alpha x square plus beta x dx, the same integral that I had mentioned couple of times before, pi by alpha e to the power of beta square by 4 alpha. All limits are from minus infinity to plus infinity. So, then you can calculate delta x is equal to x square minus x average square under the root. So, this is this minus x 0 square cos square element. So, this term will cancel out with this. So, I will get 1 over root 2 gamma, and so this will be under root of h cross by 2 mu gamma. Let me show you the temporal evolution, and then we will come back to this slightly later. So, we have been discussing the harmonic oscillator problem, and as I told you, this is just briefly going through what I have already done. So, this is my Hamiltonian, this is p square by 2m, and this is the potential energy function half mu omega square x square. This is the potential energy function corresponding to the oscillator. So, you have 8. So, you solve this eigenvalue equation, and you find that for the wave function to be well behaved, we will do this in detail, that the energy eigenvalues are n plus half h cross omega, and the corresponding wave functions are the Hermite Gauss functions. These are known as the Hermite Gauss functions. So, therefore, of the time dependent Schrodinger equation, this is the one dimensional time dependent Schrodinger equation, the most general solution will be given by this. These are psi n of x multiplied by this time are something like the modes of the system, the normal modes of the system. As you may have seen that if you have a stretched string, it has certain normal modes of the system. And these I have worked out in my book on optics. And then you displace the string in a particular way, and then you want to study its time evolution. So, you have to express this as a superposition of the normal modes of the system. And therefore, these are the psi n of x, and these are the corresponding frequencies of normal modes. So, this is how it will evolve with time. So, this is the most general solution of the time dependent Schrodinger equation. Let me come back to this in a moment, but tell you, as I had told you earlier, we have developed this software, and these are the wave functions. So, this is the ground state wave function, and the energy eigenvalue is 1 times E0. E0 is half h cross omega. let me plot the first eigenfunction. So, this is an antisymmetric function. So, the eigenvalue is 1 plus half h cross omega, 3 by 2 h cross omega. And you can see this is an antisymmetric function. The second state, which corresponds to n equal to 2. So, the eigenvalue is 5 by 2 h cross omega. So, this is the second function, second eigenfunction. Then the third, this is an antisymmetric. So, alternately the wave functions are symmetric and antisymmetric, symmetric and antisymmetric. The fourth, in fact, the fourth wave function has 4 zeros, and similarly the fifth and the sixth. So, these are the normalized Hermite Gauss functions, which are the eigenfunctions, and these are the corresponding eigenvalues n plus half h cross omega. So, this is for example, the psi 6 of x. This is a symmetric function of x. So, it is 1, 2, 3, 4, 5, 6, this thing. So, we will come back to this in a moment. So, these are my eigenfunctions. Now, as I mentioned before, let us assume a particular case that at time t equal to 0, the wave function is given by this expression. It is a displaced Gaussian. Let me tell you in advance, this is known as the coherent state of the oscillator. So, I want to, if this is, my question is, if this is psi of x comma 0, what will be psi of x comma t? And the answer is simple. I first find out seeds of n, hopefully I can find an analytical expression, and then substitute it back in this equation and carry out this summation. So, in this particular case, for this particular form of psi of x comma 0, I know I can determine analytical expression for C of n. I substitute it here, carry out the summation, and I will obtain psi of x comma t mod square is equal to this, which represents the classical oscillator. So, if I do this, this is known as a coherent state. Let me then tell you that if I superpose different states. So, I am trying to superpose two states with the following coefficient. Let us suppose the first state 0.707 is 1 over root 2 and 0.707 is 1 over root 2. So, there is a half probability of finding in the first state, half probability of finding in the second state. So, let me OK this and then evolve. So, this is how the probability distribution will dance. So, let me make it slowly. So, you can see that this is how the probability distribution will evolve. So, is the system has a particular energy? The answer is no. There is a half probability of finding E1 and a half probability of finding E2. Let me do this once again, but let me put C1 equal to 1 and C2 equal to 0, so that it is in the first state. Then what will happen is, if I evolve, it will remain the same. Psi of x comma t whole square remains the same for all times. It does not change, and that is because it is a stationary state. I hope you understand. So, let me take say 3 states. So, let me have C2 is equal to 1 and C3 also equal to 1, equal probabilities of 3 states. So, they are not normalized because there should be actually 1 over root 3, 1 over root 3 or 1 over root 3. So, the coefficients are not normalized. The software is asking me, do you want the program to normalize them? Let us say yes, and let us evolve. So, this is like this. This is how the state of the oscillator will evolve with time. Now, I go back to my coherent state and I say that let C of n be given by this. Only thing is I have to give a value of xi 0. Understand this. I then say let me choose Cn equal to so much, C1 equal to so much, C2 equal to so much, C3 equal to so much, C4 and C0 equal to so much. Let Cn be like this. It is a superposition of an infinite number of states, but I have to give the value of xi 0 and let me do that. So, that is known as a coherent state, and I choose the value xi 0 equal to 8 and I evolve with time. This is my classical oscillator. So, let me make xi 0 large, as I will tell you in a moment. Let me take it 100 and you will find that this dances back and forth. So, let me make it in little more time steps. See this. So, this is my classical harmonic oscillator. So, when you see in your first year laboratory a long pendulum oscillating like this, and you ask yourself the question that in quantum mechanics we have solved this, to which eigenvalue does it belong? The answer is it does not belong to a particular value of E. It is a superposition of a very large number of states, and these different states superpose so beautifully with time, with different phases, that the wave packet oscillates back and forth just as you would see in a classical harmonic oscillator. So, if I make it still this value of xi 0, I will explain that in my next lecture. So, then it will become even sharper, and let me make it in larger number of time steps. This is a software which is available with my book on basic quantum mechanics, which has also been published by Macmillan. So, you will see that the wave packet oscillates back and forth. So, therefore, I end this lecture by mentioning that my classical oscillator, when it is moving back and forth, to which energy does it correspond to? And I will detail it in my next lecture, that it does not correspond to a particular energy. It is a superposition of billions of states, but with very closely packed energy, closely spaced energy levels. Does it have a definite energy? The answer is no, but the spread in the energy is extremely small. We will discuss this in more detail in my next lecture. Thank you.